In this lesson, we continue with shortest path algorithms, and we're going to look at the use of the A-star algorithm to perform searches on a graph. Now, the A-star algorithm builds on Dijkstra's algorithm and try to fix the problem that it had, which is basically using a flood fill type approach that becomes very time consuming if the graph size gets big. Because you have to go through most nodes to work out the shortest path, the processing hit is quite huge. But before we begin, why is A-star actually called A-star? It's called A-star because once Dijkstra was on the scene, people in the 60s decided to refine it. They created an algorithm which was called A1. Then A1, which was using a heuristic approach, was then refined to A2. And eventually the best version of this refinement of the A series is now called A-star. That's basically the history behind it. However, let's get back to the task at hand and just check some of your prior knowledge. Hopefully you know how Dijkstra's algorithm works, how graphs are structured, and what the problem with Dijkstra's algorithm is. And if you don't know any of that, please revisit the last two lessons in this particular section. And as usual, we're going to be looking at some key terms. You should know Dijkstra's algorithm by now, which is an algorithm that finds the shortest path between 2 points or 2 nodes or vertices in a graph. A-star is an algorithm that finds the shortest path between 2 points, again 2 nodes or vertices in a graph, but it uses an additional heuristic approach to achieve better performance than Dijkstra's algorithm. So what does heuristic actually mean? Well, it's a method that employs a practical solution rather than a theoretical one to solve a problem. When applied to algorithms, this involves running tests and obtaining results by trial and error. So let's just go through the A-star algorithm in a bit more depth. Now, A-star is based on Dijkstra, but you have this additional heuristic value, which is basically an intelligent guess on how far we have to go to reach the destination. This value is already created, and in exams this will be given to you. Now, Dijkstra's algorithm pays no attention to the direction, and it basically uses a flood fill approach, which can be quite time consuming for complex problems. So this A-star algorithm's heuristic approach works much more efficiently. Because you know that the heuristic function is going to be decreasing in that particular direction, so I should be going in that direction, and it's increasing in the opposite direction, so I should probably avoid that. And to do all of this, a bit of maths is needed. So the function that was created for the A-star algorithm and the function that you need to memorize and make sure that you know how to use that with a graph in an exam is as follows. The total node cost to the destination, which is classified as Fn, is going to be equal to the home to node cost plus Hn, which is the heuristic cost or the overall distance to the destination from that particular node. Now, the function at this particular moment in time in this particular approach might not make any sense to you, but as we go through a worked example, it will start making more and more sense, and in actual fact you might find it a lot more easier than Dijkstra. So just remember the function Fn, which is the total node cost to the destination, includes home to node cost. That's the edge cost, the cost on the line, and a heuristic cost, which is Hn, which is given to you on top of a node in a graph. Let's go through an example to see how all of this works. So on screen you see a graph which has quite a few nodes. We begin at A and we need to get to J. The edge values are the distance between nodes. So for example, A to B, the distance is 6, A to F, the distance is 3. The values in green on top of node are the heuristic values, Hn, that's the distance to the destination. So how do we go about solving it? Well, straight away, the heuristic cost on top of A basically says that to get to the destination, the heuristic cost is 10. So you know that path will take about 10. So if you get this particular one, it's very easy to work out what the path is going to be anyway. But sometimes they don't give you that value on top of A. That's the one that you need to calculate. But they will give you the heuristic value for all the other nodes. So our first step is to make sure we create a table like the one on the top right hand corner, where we write down the following headings: node, home to node cost for that node, which is Gn, the heuristic cost, which is on top of the node, Hn, and then the total cost, which is basically Gn plus Hn. Once we got these headings, let's begin by writing the first node A. We're there. There is no home to node cost because you're actually there. The heuristic cost is 10, so the total cost is 10. We highlight this A because this is the starting point. Next, we work out the two nodes that are connected to A, in this case B and F. Now you can pick whichever one you want to go with first, that doesn't matter. So B has a home to node cost of 6 from A, and the heuristic cost on top of that is 8. So the total cost is 8 plus 6, which is 14. Then we do the same thing for F. The cost between A and F is 3. The heuristic cost from F to the destination is 6. So the total cost is 3 plus 6, which is 9. Now since F is the lowest total cost out of those two, we highlight F, and then from F we work out the next two connecting nodes, which are G and H. So for G, the home to node cost is 4, and you will say, well, how did that work out? F to G is just 1. Well, if you think about it, A to F is 3, and from F to G, it's an extra 1. So from A to G, the total home to node cost is 4. And then you simply add the heuristic cost, so 4 plus 5 gives you 9. And similarly, we can now work out H. The home to node cost for H is 7 plus 3, which is 10, and that's the distance from A. And the heuristic cost is 3, so 10 plus 3 is 13. We now highlight G as it has the lowest total value between G and H. From G, it's pretty straightforward. The next node is I. There is no other option. So in this particular case, the home to node cost is 4 plus 3, 7. Because that's the distance from A, you add 1, which is the heuristic cost for I. So 7 plus 1 gives you 8 as the total cost. And we highlight I as the one with the lowest value because it's the only one. From I, we can get to 3 particular nodes, H, J, and E. And we do exactly the same thing. So for J, the home to node cost is now 10. Because I was 7, so you add 3 to it, so that's 10. There is no particular heuristic cost because this is the final destination. So 10 plus 0 gives us a total cost of 10. And similarly for E, we can work out the home to node cost of 12 plus the H cost of 3, which gives us 15. And for H, the home to node cost is 9 and the H cost is 3, so 9 plus 3 gives us 12. Now comparing these three, J has the lowest value, so we highlight J. And since J is our destination, we can now simply go through the highlighted paths to work out our optimum path. So that path is A, F, G, I, and J. And if you add the cost of all of the nodes that connect them, 3 plus 1 plus 3 plus 3, that adds up to 10, which is equivalent to the total heuristic cost of A in the first place. And there's no other path that can lead you to 10. If you wanted to check all the remaining paths, you could probably use a brute force approach and check them and add them yourself. These type of graphs are very small, so it's easy to do that. But in the real world, often when you will have hundreds and thousands of nodes, it can become a bit more tricky. So this algorithm really helps. So this one's over to you. Try to find the shortest path between home and school using the A-star algorithm. Hopefully the algorithm makes sense. And once you arrive to a solution, feel free to share that with me. That's all from me for today. Hopefully you now know the function behind the A-star algorithm. You can also understand the difference between A-star and Dijkstra, the use of a heuristic value that allows it to take a directed approach which eliminates the flood fill problem that is quite common with Dijkstra. And you can also use the A-star algorithm, or in particular the A-star algorithmic function, to work out the shortest path between two nodes on a graph. That's all for today. If you do have any questions, please do get back to me. Otherwise, I'll see you in the next one.